And she works in surface water hydrology with a lot of, in surface water they had this big worldwide project on the prediction on ungauged basins. So she was very active in that project. She's been working on Bayesian estimation and certainty reduction and these kind of things. And I guess that this is Ungauged Catchments, huh? So this is what she's going to talk about today. Cristina, the floor is yours.
Thank you, Jesus. Thank you very much for this nice introduction. So, yeah, today I'm going to talk about the work we have been doing in advances in hydrological model prediction, model identification or selection in Ungauged Catchments. This work hasn't been myself only, so I have been collaborating with some key people, so I cannot name every single person here, but I would like to thank some of them, like Dimitri that is here, or Fabrizio and Andreas that was doing my postdoc in EABAC, and my PhD in Imperial College Santander and NCAR, and in the University of Bristol, and then some collaborations that also Jesus was involved with for summer schools, and currently we are working also with people from ETH like Geochemistry. So first, I would like to give just a bit of background of where I came from, or just introduce it a bit, and then I will move for predictions in Ungauged catchments, and then about how we select model structures for different catchments. So I work in IHCantabria nowadays since 2008, and my institution is the Georesearch Institute between the University of Cantabria and the government of Cantabria. So we work both in consultancy and research related to water problems. Our initial focus was in coastal. We were quite strong, and we are quite strong in coastal. But in 2008, was when I was hired for, we opened the research line in hydrology, and it was my main task, basically. And actually, this year we received the Leonardo Torres Quevedo National Research Award. So my PhD, before my PhD, I was working in consultancy with mainly focusing hydrology and flood risks for international clients, or also national clients like in the American Bank of Development or the World Bank, Pacific Bank. And then I pursued my PhD about improved predictions in Ungauged catchments using Bayesian inference. Then I came back to Santander, where I started to open this research line in hydrology, but with the focus in model improvement. And in IH, we merged research with knowledge transfer, which is kind of consultancy, and teaching also. So we have to cover these three areas in this. And I did my postdoc about reducing hydrological model structural certainty in EABAC in Switzerland. And then now, since 2022, well, before I was already collaborating since a long time ago with Dimitri and Fabrizio and Prieto, and since 2022, we are focusing more in improving early time scale predictions. So this is just to illustrate some kind of schools that we have provided. So this school was about probabilistic predictions, summer schools we organized, and some information theory workshop and schools that Jesus was also involved. And this is a selected consultancy project, well, it's more than 28 cities now, about that provided my main motivation to move to Ungauged catchments. So the first project we have, now we have covered all of them, but it was risk analysis in Trujillo in Peru, and the first problem I think I faced was the lag rate. So this motivated me to pursue my PhD in predictions in Ungauged catchments. I just also wanted to tell you that my main topic is modeling the catchment scale. So we are not using distributed models now, we are using Lambda models and conceptual models, basically, that they are not process-based. They are process-based models, but there are some conceptualization. And we work at catchment scale. So the first scientific part of my talk, let's say, is about the model adequacy tests that we developed to for improving predictions against catchments. And this paper was in collaboration with Dimitri and has been published in in WR. So just to provide a bit of motivation, a successful water planning and the economy based on it depends on being able to make reliable predictions of hydrological resources. In Ungauged catchments, we usually have, we have observations, so we can use traditional calibration techniques. But in Ungauged catchments, observations are not available. So we need to implement techniques to transfer the knowledge that we have in the Ungauged catchments to the Ungauged catchments. This is basically what regionalization does. And in the Ungauged catchment, we could inform the parameters of the model in the Ungauged catchment based on the regionalized flow indices. And this is an important topic because of the vast majority of catchments in the world are ungauged. So this was at the beginning of the project. The catchments we selected at the beginning for the whole of Spain, but then we focus in the catchments in the north of Spain where things will come there. As whatever kind of technique, sources of uncertainty or error in the regionalization procedure came from different sources. For example, in the inputs, so we are not sure about our rainfall or our potential aspiration, but also the observations we use to evaluate our methods. We also have uncertainty coming from the model structure, because of when we use a model, whatever model we use, we are unsure about not only the parameters of the model, but also if the structure, the conceptual structure of the model. But at least the model structure can simulate hydrological hydrographs, and then we can summarize these hydrographs using signatures or flow indices. For example, a flow index is the mean annual flow. So, but in Ungauged catchments, we also have the problem related to the regionalization model. So in an Ungauged catchment, we don't know actually, in principle, what flow indices or hydrological indices we should pick, which are most informative. What is the related, what catchment descriptors, and a catchment descriptor can be the area or the slope, we should pick up also. And what is the relation between these catchment descriptors and the flow indices. So hopefully, what we expect is that when we condition a hydrological model on the flow indices, ideally, the Ungauged catchment, this we can propagate into the hydrological model and obtain predictions that are similar to the actual stream. So we need to test the models in the procedure in Ungauged catchments, treating them as Ungauged. Yeah, and I would say that also the hardest to characterize is model error. And what I mean with model error basically is the structure, our conceptual structure of how the inlet catchment works. So in this work, we have mainly three objectives. We wanted to improve the state of the art of the Bayesian predictions in Ungauged catchments with respect to the new advances in the treatment of hydrological indices. So hydrological indices, flow indices, and signatures are the same name for the same thing with different names. We wanted to develop some tests that could tell us a priori if a model should be adequate, would be adequate in principle for an Ungauged catchment because of a hydrological or regionalization. We have two models here. If the model is found inadequate, the model is parsed to the fork to estimate the parameters. And then we wanted to evaluate our model adequacy tests and also identify the main source of error where we have to input more, to invest more resources. It was the hydrological model or it was the regionalization. So I want to provide kind of background about how we model this. So let's assume we have a deterministic model, H. A model has a set of parameters, theta, input x, and the initial conditions. And we can simulate hydrographs, okay? Then we have a set of catchments where we have observations and an Ungauged catchment in this set of catchments. In the catchments, we have observations, we have the catchment descriptors, we have the observed stream flow, and we can summarize the observed stream flow, the flow indices, and even we can compress these flow indices, projecting them into principal components and using some kind of method like rock and stick to select the most informative. So we have, again, this set of gauge catchments and one ungauged catchment where we have the catchment descriptors, but we don't have a stream flow, and we want to predict the stream flow here. So how we did, and what is a regionalization model? So we construct a probabilistic regionalization model relating the catchment descriptors with the flow indices in the gauge catchments. So the x-axis means the catchment descriptors, the y-axis refers to the flow indices, and as with whatever model, you estimate the deterministic part, and then you have an error from the deterministic to the actual observation. We can do that for all observations, and we can estimate the distribution of these errors, which characterize the error from the regionalization. And then, in the ungauged catchment, because we have the catchment descriptors, area, slope, this kind of descriptors, we can apply the regionalization model to obtain the flow indices. So we developed one adequacy test that includes two parts, basically. What we call distance test and info test. The distance test is basically quantifying whether a model, regionalization or hydrological, is able to capture the information we have in the gauge catchment, or in whatever information we have. In this case, it would be, is the model likely to reproduce the regionalized information? And why is important? Because if you find that your model is not able to reproduce the information, the flow index is already there in a gauge catchment. You don't need to continue with that model. So these ellipses represent the joint distribution of the flow indices provided by the hydrological model, for example. And then the yellow contours is the 95% of probability of the information to be inside. For example, if the regionalized information is inside the yellow part, it's meaning that there is a 95% of chance that the model includes or represent or reproduce the regionalized information. If it's out, we don't pass. We say we don't pass the distance test. But if it's in, okay, we assume the model, well, it's 95% of chance the model passes the distance test. But it's not only important if the model is able to reproduce the information. It's also important how much information is added a model over your prior knowledge. Because if the model does not have any knowledge about your prior knowledge, you don't need a model. You can use just your prior knowledge. And for this, we developed what we call the info test. So in this plot, basically, the x-axis is the realized information. These are probability distributions, but basically means that what is the probability of obtaining the realized information given by the hydrological model or our prior information. So if our prior information is higher than the knowledge of the prior model, then the test is failed. And if the bell shape, so if the model, the hydrological model is having more information than our prior information, the test is passed, and then by factor is over 1. So a model is considered adequate if it passes both distance test and info test. But and it could be a priori used in the next step, which is flow predictions. But if the adequacy test has failed, we should revise our hydrological model selection and or our realization procedure. So this spares a lot of time from the model to later sampling from the model predictions. So if the model passes the adequacy test, we use Bayesian inference to infer the parameters of the hydrological model in a gauge catchment given the information we regionalized and the error from the regionalization. And then when we have the streamflow simulated in the Ungauged catchment, we also can simulate the prediction bounds, use sampling from the posterior distribution, which if the model is found inadequate, reduce the amount of time lost. But we also wanted to evaluate not the model not only in the flow signature space, but also in the time series space. And for that, we used the probabilistic cycling. So basically, it's a metric that combines accuracy and precision. The accuracy quantifies the distance between the expected value of the distribution and the observations, and it's the same as the deterministic part of the deterministic cycling. But we penalize with the variance, the precision, which quantifies the spread, not only the distance to the observations, but also how spread distribution. And then reliability represents the consistency between the observations, the predicted distribution, and the observations. And we use the 95%. So if the observations are in the 95% of the posterior limits, it's something like this. As I told you before, in our case of study, we focus in the north of Spain catchments, and we have 92 natural catchments there, where we could calculate 103 flow indices based on mean annual flow or mean monthly flows. So a flow index is something that you can compute from hydrology, our summary statistics mainly. And then we selected 16 catchment descriptors. The model we used was PDM, that is a pretty standard model, conceptual model, buckets model, used it in the UK. It was when I was doing my PhD. And we treat the red points, which are catchments, but we treat them as Ungauged catchments to test our methods. So also I wanted to refer that instead of using flow indices, we projected these 103 flow indices into principal components, and then we reduced the dimension of the flow indices to 4 principal components that we found were the most significant. So these 4 principal components explained 88% of the variability in the flow indices, and our realization precision was between 10 and 16%. And these are just examples of the residual error for the realization. It's also to illustrate that they were not all Gaussian. So the first principal component, the errors in the first principal component were Campbell. The second and the third were correlated and were 2D Gaussian, and the fourth one was a 1D Gaussian. So we look at first how the behavior of our adequacy tests, so in the flow space, index space, not in the time series. And we found, so we tested in case study name or experiment S0, where we assumed and we had the observations. So this allowed us to test individually if the hydrological model was able to capture the observations in the catchment, the observed flow indices, and also if the regionalization model was able to capture the observed flow indices individually. And we found that the hydrological model passed only in 3 out of the 16 catchments, and the regionalization was adequate in 12 out of the 16 catchments. But this is not possible, of course, in Ungauged catchments because we don't have data. So this was kind of proof of concept. Then scenario 1 was the intended usage of the method, where we test whether the hydrological plus regionalization model passed the adequacy test, and we saw that it only was adequate for 1 out of the 16 catchments. So then we asked ourselves what happens if we reduce the different minor components of error here. So we moved into improved regionalization. What is improved? Improved basically is that the regionalization model could reproduce the observations, but with some errors, some noise. And we found the hydrological model was not adequate, which is kind of a relief because of this regionalized component is like the observation, but with small with a small noise, and it deteriorates further what we have in the observations. And then we replace the predictions from the hydrological model with the observations and use the original regionalization model. And we found that when the hydrological model was exact, the hydrological model passed the adequacy test in 7 out of 16. So the hydrological model was adequate in simulating the observations, but was not adequate in simulating the regionalized information. And then we asked ourselves what happened if we first improve our hydrological model, and then we reduce the error from the regionalization. And then we found that in 12 out of 16 catchments, the hydrological model passed the adequacy test. And based on these results, we conclude, we will see the conclusions that the main source of error between realization and the hydrological model was the hydrological model structure. So here is just to illustrate that in the catchment we found the hydrological model was adequate in representing the realized flow indices, improving only the regionalization or only the hydrological model did not have a big improvement, make a little impact on the streamflow predictions. But when we improved first the hydrological model and then the regionalized procedure, we saw a huge difference in the time series predictions. And again, here we are conditioning a hydrological model with 4 summarized indices, and we are testing in the flow space. So still are aggregated metrics. And this is to illustrate one of the catchments where the hydrological model was inadequate. And when the hydrological model was inadequate, improving only the regionalization does not lead to a systematic improvement. It can be worse of the predictions. But when we improve again, first the hydrological model and then the regionalization procedure, we got very high quality predictions. So our conclusions were basically that the new adequacy tests for the hydrological and the regionalization model can serve ourselves to test whether a model can reproduce the flow principal components in this case, what information you have in the catchment, and how much information is added by a model over the prior knowledge. And we think the adequacy test can guide the model improvement process. So if the model passes the adequacy test in principle, it can be used for flow predictions. But if the model fails the adequacy test for disaggregated flow indices, we should improve the regionalization or the hydrology. And yeah, we claim these are necessary but insufficient conditions for a model to be able to make good predictions, reliable predictions. In the key case studies, what we saw was that the first 4 principal components were enough to summarize or contain enough information to summarize the information from the 103 hydrological indices, and that the priority should be given to improve the hydrological model structure and then the regionalization, but not the other way around. So this also motivated our next work, our next paper, about if the model is the hydrological model is the main source of uncertainty in this case, so this is what we saw basically in our case studies, how to select or how to identify a suitable model. Okay? So this leads us to hypothesis testing to identify dominant hydrological mechanisms in ungauged catchments. So when we identify those mechanisms, we can select more. And this has been also published recently in IHCantabria. So as we have just seen, hydrological modeling of ungauged catchments is a major practical and scientific goal in hydrology. And the key challenge is how to identify a model structure reflecting the hydrological processes of interest in Ungauged catchment. In this case, we wanted to develop a hypothesis testing method to identify the dominant mechanisms in Ungauged catchments using the regionalized information as inference data. And in this case, we evaluate the performance of the method using the identifiability and the reliability that I will explain a bit later. And we tested our new method, let's say. We're using real and synthetic experiments. With the real data, it's the intended usage of the method, and with synthetic experiments, we can explore what happens when we modify different sources of error. Again, our case of the study was the 92 catchments from north of Spain, and 16 of them were treated as Ungauged. So here I want to provide some kind of definitions what is about an actual process, a hydrological model process. So what we call for a process in a hydrological model. It tries to represent the physical phenomenon occurring in a catchment. And we have different, for the same process, we have different parameterizations to approximate that process in the catchment. For example, a process could be the surface runoff generation, and you can approach such process using a power of addition, like the one model, BIC parameterization, or use another function, like top model parameterization, that use the distributed topographic index. So this means that for the same process, the surface runoff or the percolation, you have different mechanisms, so different ways to parameterize that process into the hydrological model space. So it's not the real space, the model space. If we combine one mechanism per process, it's when we have a model structure. And well, here, what the flexible model modeling framework makes is basically that allows to combine different mechanisms to create different model structures, but the set of processes in the catchment is fixed a priori. So once we have the flexible modeling framework set, which is an ensemble of models, we can simulate hydrographs. And the sizes of these boxes indeed try to represent the amount of information we are losing when we are compressing information from the whole hydrograph to flow indices and then to the most informative principal components. So we can simulate hydrographs again in the catchments. We can simulate the flow indices, summarizing these hydrographs. We can project them into principal components, and we can reduce them. But in the Ungauged catchment, we also have the catchment descriptors, same as before, the area, the slope, the OE, so we have the regionalization model. We can estimate the flow indices, and we can also map them into principal components, and we can relate, using likelihood function, the simulated and the regionalized principal components. Based on what is more likely a posteriori, we can identify whether the mechanism is dominant. So whether parameterization for a single process is more likely than others. Our performance metrics in this case were the fraction of identifications, and basically this means that if we identify something dominant or not. So, for example, in the surface runoff process example, if we have two equations to approximate the surface runoff process, can one of them be more likely than the other? So more likely than the other or not? But this is not telling if we are correct identifying something. It's just if we are identifying something dominant. So we also need what is called reliability, which is basically if the identification is correct. However, in Ungauged catchment, we don't know the truth, so we only can test this in the synthetic cases where we know which is the actual mechanism. And the fraction of identification of reliability varies between 0 and 1. So for 0, nothing is identified and is not reliable. And if the fraction of identifications is 100%. So we identify a dominant mechanism, but it's only correct if the reliability is also 1. So we tested our 92 catchments, and we used the 16 catchments as engaged. So in this plot, basically, this is the map, let's say, for the north of Spain. The cycles are the 16 catchments. The bigger cycles is in one experiment, what we call experiment 1, where we have the realizing information and the hydrological models provided by the ensemble. And then the field cycles means that we identify something, one mechanism as dominant. And the inner cycles are for the case where we improve the realization. Here we use real data, so we only could look at what was the dominant mechanism, or for what process the dominant mechanism was more likely identified, and least identified. So for the surface runoff and the routing, we identify where the process for which we would identify most frequently a dominant mechanism. But for unsaturated zone and percolation, we did not identify any dominant mechanism in any of the catchments. We could not. And then we used synthetic experiments to analyze the impact of the realization error. So, for example, if the realization error was 1, means that it's the same error as in the experiment 1, where it was the original realization. But by the way, it was random forest, but model that could be other realization. If the error is 2, basically we are so bad with the realization that we are even doubling our initial error. But if it's just 5%, the error in the realization was quite low. So what we find again is that the fraction of identifications were the lowest for the percolation and saturated zone, and the highest reliability was for the surface runoff and for the saturated zone. The fraction of identifications in general for the synthetic case was 27%, which was similar to the case using real data that was 25%, and our reliability varies between 0.6 and 0.9, 35. Then there were some processes where we improved monotonically the fraction of identifications when we reduce the error in the realization, and but there were others for which it couldn't. And in terms of reliability, we saw that it improved when the error in the realization was reduced. But this is using only for pieces of information. So in our conclusions, we developed the hypothesis testing method to identify dominant mechanisms for process representation in Ungauged catchments. Again, the least identifiable processes were the percolation and the saturated zone, and the process for which we identify dominant mechanism more frequently were the surface runoff and the saturated zone. When model error decreases, the overall reliability increases, but the fraction of identifications remains relatively constant. And this low amount of fraction of identifications we attributed to the low amount of information we used to inform the mechanisms. And we also noted some mechanisms interactions. Yeah, and here is some key references to this work I have already mentioned, and to the work that were kind of related. And yeah, thank you very much for your attention. If you have any questions, I'm happy to ask.
Okay. Question?
Very interesting presentation, so thank you very much for this.
Thank you.
This is an issue. I am interested to know how you include information of extreme events in this kind of catchments that you don't have. You were mentioning about the lack of data. Well, lack of data. Is this saying I came from Panama and we have these things? So I want to know how you can improve this using this methodology that you were mentioning.
You need to analyze the error distribution in the for the extreme events. Basically, I'm not sure if you are using for floods, I guess, for Panama.
Yeah.
So you need, I think, to look at the topest streamflow. You can use different approaches, or use the threshold, okay, and use basically boom some distribution, and estimate the residual distribution for the higher rates. But the heavy tail distributions have other problems also when you try to optimize the parameters of the Campbell or GEV. So I think I have not used for extreme events in South America, but I think it can be done just looking at the age catchments that you have in Panama more than in other places, and then estimate the residual distributions, and then you can inform the parameters of the hydrological model, identify the hydrograph that you want to use for the floods, I guess.
Thank you.
I have a more basic question. Here you'll be comparing regionalization models. Can you describe your regionalization models?
Okay. So in our case, we use a random forest model, and in PATH, so PATH is prediction against catchment decay. They used to stop using linear regression models, but we did not go for linear regression models.
Linear regression of what versus?
Catchment strict. You can do, there are different types of regionalization, basically. You can regionalize flow indices as we did. You can regionalize parameters as what was trying to do before. But when you regionalize the parameters of the hydrological model that has been previously calibrated in a set of catchments, you are dependent on the hydrological model you are calibrating for each of these donor catchments. So instead of transferring hydrological model parameters from gauge to ungauge, we transfer flow indices for mineral flow and so on that are not dependent on the hydrological model, are dependent on the measurements you have in the catchment, in the gauge catchment. That was the first thing. So there was two currencies in the two movements in the realization bubble. One was transferring parameters and the other was transferring hydrological indices. Based on what we saw before, we decided to transfer hydrological indices. How to transfer these hydrological indices? Before we introduced the random forest in this work, it was done with regression, a linear regression. But this forces you to assume that the errors are Gaussian. While if you are using random forest, you don't need to, it's more flexible, much more flexible. You don't need to assume any prescribed distribution like you are going to be Gaussian or something like that. That was one of the motivations to use this random forest. And this was also used in the eco-hydrology community by, I think, Snelder. Yeah, Snelder. But they did not regionalize the principal components, which, yeah, some hydrologists claimed was not too much related to the domain size, but it's true that it allows to compress 103 hydrological indices into 4, so you can figure out also the amount of information you are losing, and you are estimating the error. So we are not comparing different regionalization procedures. We pick up the random forest one, but we pick up that procedure because it was much more flexible in terms of the error distribution. And we did not regionalize parameters, we regionalized flow indices that are related to the observations in the gauge catchments and not to a prescribed hydrological model that even is worse because you use the same hydrological model for all catchments before you use the same hydrological model for all catchments under analysis.
I name the question. I repeat the question. So on which basis did you realize?
So the catchment descriptors that include
No, I don't want to know the output, I want to know the input.
for the realization. So we have what we call catchment descriptors, and catchment descriptors that are basically soil types. They cover the topography, soil types, vegetation, land uses, climatology. So for example, when we have 30-something, 32 or so, and we use Pearson correlation to pick up the less correlated. We use it 16. And they were the area, the slope, I think the percentage of coniferous forest. So,
No geology,
no, the soil type, but,
only soil type.
and the lack of data for sure, this is why I was wondering why is not, for the 624 model structures we ran with 1,030 parameters and so on, for none we identified dominant mechanism. And a mechanism was more likely to happen for percolation than saturated soil. And that's again, or the lack of information comprised in these indices, or the model structures representation for the percolation and the processing and saturated soil was too simple.
But you have no model to use, if you realize the indices, you have no model.
Excuse me, so I didn't put the flow indices. So the flow indices were, the 103 were representing the mean annual flow. So monthly, basically it was expected values or mean values and variance of annual and monthly flows, the day of peak flows. So some summary method, whatever summary method you can have from the hydro. And this is what is realized, flow index. So what is the probability of the parameters of the PDM model given the realized principal component, or more simple, okay? Given that the mean annual flow was this one. So here you have to problem, basically. You have to problem or correlate. The problem, because of your conditioning, the parameters of the hydrological model. So,
But I don't see where they can enters.
no,
I mean, if you are transferring flow indices which come directly from hydrographs,
so here. So we have the realized flow indices. Let's think simple, okay? Like realized mean annual flow. So, and we have a likelihood function. We estimated in the gauge catchments the likelihood function by estimating the residual distribution between the regionalized and the simulated flow indices. So you have flow indices in the gauge catchments, and you can regionalize them until then is clear more or less, or you are in the regionalization part, asking. So how?
I don't know what this has to do with the ocean, but that's okay. That's okay. I probably.
You mean how to condition the hydrological model parameters on the regionalized information?
The point is, if your prediction of engagement is based on transferring flow indicators, I don't see what the model enters into there. So you, I mean, okay, so you have a parameters here, probability of meters, condition of some things. But that means that you have built a model where this is a model of the engaged basins based on the realized
Information, and we assume that the error in the payment model is in the realization would be the main or similar or the same as the error in the simulated streamflow by the hydrological model. This is probably what you are used. So the error distribution were developed in the gauge catchment. But treating one of them like a gauge, using that might be the strategy, leave one out strategy. And you have that error distribution, and we assume that that error distribution is the same as the likelihood function here. And this is where the hydrological model comes in.
But at this stage, this seed rate are no data.
Set reg has been already estimated. Yes.
They are not data, this is a regression.
Yeah.
So
you have the estimation, and you have the error, the likelihood function is this one.
okay, now I understand what you're
So this is the likelihood function, and you
I don't believe it. Okay, now I understand.
okay,
It's kind of a mental exercise. So you project the data from an engaged basin, you generate data from an engaged basin,
yeah.
and then you calibrate the model against this data and identify the processes of this model. Yes.
Okay, that is in the second one. Yeah. Using as inference data the generalized information.
Which is not information.
No.
Okay,
This model is data from a model. No, it's not observed.
Yeah, okay.
So this have error. You have error because of the realization. So you have the realization, what you are feeling is what it is basically.
But believe, I understand my point. Greek hydrology will not come here, because in Greek hydrology, you need the geology, and when you have car, you have no river, blah, blah, blah. It is not here, because you don't have the casting nature of basins.
No.
And then you're based on that, you're going to tell me if percolation is important in the Greek basin or not, even if, you understand my point?
I think you
Greek
could.
basins have no rivers because they are karst, the geology is such a problem. In your regionalization, if you don't account for that, you're going to miss it. And therefore, whether percolation is important or not
Exactly.
important is so much dependent
On the
on the regionalization scheme that
and the catchment descriptors included. The catchment descriptors, so the geology, this was
Yeah.
related, so again, it's not just the realization model, it's the inputs to the realization model, which are this geology, soil types, and so on. And yeah, I think this is the main problem about we need those data, but as we have basically more specific ones. We do databases, general databases for Spain, but that is our guess, that the information was not enough for some of the processes, and they are related to the soil processes. For the surface runoff, was no, but not for the ones. So you were right.
Well, I mean, it's just to understand. I see the point, but there is, especially this particular conclusion is so dependent on the regionalization scheme that
But here, this is why we tried regionalization with lowest amount of error. And we still had the same amount of identifications and same poor identifiability for those two processes. And this is what you are telling. If you are,
really this is another issue. This is.
but if you're not including, if you're not including in the inputs, the most informative, let's say, for percolation and saturated zone is not going to capture, which is correct, I think. So we did not include in the catchment descriptors. And we used the general database, and I think they were not so specific. Also, I guess it's not, I don't know how feasible it is to get measurements for geology and for soils in these catchments. I agree. I mean, I think this is why our conclusion was about the relatively low identifiability, so for those processes. It's attributed to the low amount of realized information. This amount of realized information comes because of the catchment descriptors, let's say soil types and geology were not enough. But again, it's only 4 pieces of information. We are not.
I think a little bit related to that, when you say data, Does it also include rainfall data, meteorological data, or?
For the regionalization or for the local
Or
model?
for both?
Okay, so for the regionalization, it's climate data, so yes, it covers rainfall, but climate, mean are more aggregated. And for the hydrological model, it was daily rainfall, so to come. First point, we say that the main sources. Yeah, so the priority should be given to the hydrological model and its inputs. This was when we compare regionalization versus the hydrological model to estimate not mechanisms but the flow time series, surface. Okay. So the inputs were potential precipitation and rainfall. They agree rainfall is with average rainfall based on rain gauges.
You can have flooding or events with
Yep.
you mentioned.
Yep.
But this data is inferred from maybe Gs, or is something that's taken from the field work or something like this?
So the rain gauges were from the potential precipitation, I think, what like hard graphs, some equation.
Yeah, because I know that some problems in the runoff models is the origin of this data. Like, now that we are improving the use of Gs and Ds, we are trying to avoid the field work that maybe this is the lack of. No, it's not avoid, it's just like sometimes in the time of concert.
Exactly. But so the rain gauge, for some of the catchments, we have one rain gauge. And for others, maybe two. So, and you have to interpolate or do an average or kind of, and this is why we're aware of that, right? So that type of error. And the other type of error is your conceptual model. It's like cognitive bias, basically. How do you build a model? What processes you include, and how do you approach each of these hydrological processes that are included in a model. What was kind of nice thing was that the realized information here for the simulating hydrographs was enough, let's say, but realized information was not enough to describe the single processes into the model. And the GIS data we use for the catchment split. So, like Minas, Instituto Geológico de Minera, España, but also some of the GIS data were 25 square kilometers. And I mean, this is the data you have available. But also, for example, for the soil types on the geology, I think there were not enough. I mean, it's clear that the surface, the processes related to the surface water were.
It's important to consider this data. So
I think so. I think, yeah. I mean, this is why I was always asking indeed what was kind of dominant for the percussion. The other hypothesis would be like the conceptual models we have in the mainly surface runoff. That's what describe maybe enough the process in the unsaturated zone. So that was the other. But I think the data is probably the main.